Year 13, Chapter 9, Further Differentiation, Lesson 2, Differentiating the Natural Logarithm Function. So we're going to start off by learning how to differentiate y equals ln of x. And so we need to start off by reminding ourselves that the function ln of x and the function e to the x are inverse functions of each other. So I'm going to start off by saying, let's have y equal to ln x, and our aim is to differentiate y with respect to x. So our aim is to find dy by dx. Because then we would have differentiated ln of x with respect to x. Now, here's how I'm going to go about this. I'm going to take e to the power of both sides. So I've got e to the y on the left-hand side, and on the right-hand side I have e to the ln x. Now, what do we then know? Well, we have e to the y equals x on the right-hand side, because as we've said, e and ln are inverses of each other. So I have x equals e to the y, and I'm actually going to write it round that way. And I'm now going to differentiate, but I'm going to differentiate with respect to y rather than with respect to x, because this is written out in the format x equals rather than the form y equals. So we're going to differentiate with respect to y. So what do we get? We're differentiating with respect to y, so we get dx by dy. On the right-hand side, the function is in terms of y, and we're differentiating with respect to y, so we get e to the y. So we have dx by dy. Now, if we then want to find dy by dx, we need the reciprocal of dx by dy, so it must be equal to 1 over e to the y. But what do we know about e to the y? It's the same as x. So this gives me the information that dy by dx is equal to 1 over x. And this is the crucial piece of information. The derivative of ln of x is 1 over x. So let's have a look at a few examples. Y equals 5 ln x. So the 5 here is just a multiplicative factor. And when we differentiate this, we get dy by dx equals 5. And then differentiating the ln of x gives us 1 over x. So the answer is 5 over x. Now, let's look at a slightly more interesting example. Y equals 3 ln 4x. Now, there are two methods that we're going to use to differentiate this. Method 1, which I'll do up here. We're going to use the chain rule. Now, can you recognise that this is a composite function? We have 4x as our inner function, and we're then taking ln of that. So the chain rule can be applied very simply here. So u equals 4x, and then we can express y in terms of u. Y equals 3 ln of u. We then need to differentiate both parts, so du by dx is equal to 4, and dy by du is equal to 3 over u. That's no different to differentiating y equals 5 ln of x, which we did a moment ago. We know that ln of u will differentiate to 1 over u, and the 3 is just a multiplicative factor, as we've said previously. Then the chain rule tells us that dy by dx is equal to dy by du multiplied by du by dx. So what can I substitute in? Well, I know that dy by du is 3 over u, and then I can replace du by dx with 4. But what I'm now going to do is replace u with what we know u is in terms of x, and it's 4x. So I've got 3 over 4x multiplied by 4. Now look what happens here. Can you see that the 4's cancel? So even though the original question had a 4x here, the final answer for the derivative is just 3 over x. And we can see this using another method to differentiate this. This time, what I'm going to do is leave the 3 alone, and I'm going to take this part here, ln 4x, and I'm going to rewrite it as ln of 4 plus ln of x, 3 being the multiplicative factor outside, using a logarithmic rule. I can then expand, so we get y equals 3 ln 4 plus 3 ln x. Now, differentiating dy by dx, well, let's focus on the two parts of this. This is a constant. Now, what do we know about constants? They're just numerical values. There's no x component to this. It will differentiate to 0. So the only part that will contribute to the derivative is this 3 ln x, which we know will differentiate to 3 over x. So again, we get the same answer, and notice that 4 is not present. So this tells us that if y is equal to ln of, let's say, px, where p is some sort of constant, well, we're not going to see p in the derivative. dy by dx will just equal 1 over x. So what have we seen so far? If y equals something as simple as ln x, this tells us that dy by dx is equal to 1 over x. If y equals k ln of x, where k is some constant, then dy by dx is equal to k over x. So you'll see this multiplicative factor k appearing in the derivative. What happens if y equals ln of ax? Well, dy by dx is just equal to 1 over x. So notice that the a plays no part in the final answer. So the most generalized way of expressing all of this is to say if y equals k multiplied by ln of ax, where k and a are constants, then dy by dx is equal to k over x. And you need to be fully aware of the fact that the a will not appear in the final answer. Now again, if you want to see what happens to the a, look back at the previous example where we used the chain rule to differentiate ln of 4x. It effectively cancelled out. The 4 effectively cancelled out, so we were left with just 1 over x. So we're now going to have a look at an example involving the chain rule. So let's write out the function that we are going to be differentiating. We're going to differentiate y equals 2 ln 5x minus 1. Can you see the composite function here? Can you see the inner function, which is 5x minus 1, and then we take ln of this. Now, we're going to do this in two ways. We're going to use the long format of the chain rule, and then we're also going to have a look and see whether we could do this using the quick chain rule as well. So using the long form of the chain rule, I've identified the inner function as u, which is 5x minus 1. So I can now say y is equal to 2 ln of u, writing y in terms of u. Here's the differentiation. Du by dx is equal to 5. And dy by du is equal to 2 over u, now that we know how to differentiate a simple ln function. Making use of the chain rule, dy by dx is equal to dy by du multiplied by du by dx. So that's 2 over u multiplied by 5. So that gives us 10 over u, which gives us 10 over 5x minus 1. Now, interestingly, in this question you can see there's a 5 here, but it's part of a broader inner function, 5x minus 1, and consequently we see the whole of the 5x minus 1 in the final answer here. So, how could we use the quick chain rule? Well, it relies on us knowing that if we have ln of something, this effectively differentiates to 1 over something, but we do have to just adjust a little bit carefully. So let's start again with y equals 2 ln 5x minus 1. Now please remember that this 2 is purely a multiplicative scaling factor here. dy by dx will feature the 2. And then I look at the fact that overall this is an ln function. And I know that ln functions differentiate to 1 over. So it's going to differentiate to 1 over 5x minus 1, 1 over something. It's ln of something, it differentiates to 1 over something. But of course, we need to multiply by the derivative of the inner function, which is this step here in the chain rule that we've already seen when we use the long format of the chain rule. What's the derivative of the inner function? It's 5. Now combine these components together and we have 10 over 5x minus 1, which is the answer that we have here as well. This continues the pattern of the quick chain rule that we have already seen in other examples. So here are 2 examples for you to try yourself. If you want, you can work through the question using the video, or you can have a go yourself and then check your answers. Now, both of these are overall ln functions. They are ln of something. So let's take a look at the quick chain rule. dy by dx, remember, if there's a multiplicative factor at the start, it can just be part of the answer. ln of something will differentiate to 1 over the something, but we need to multiply by the derivative of the inner function, and the derivative of the inner function here is negative 2x. So as simple as this, I can put my answer together, negative 12x over 3 minus x squared, and we're done. Now let's approach the second example in a similar way. Y equals ln of root x, or y equals ln of x to the power a half. Again, it's an ln function, ln of something. Doesn't matter what the something is, it's ln of something. So it will differentiate to 1 over the something, which is 1 over x to the half. But I then need to multiply by the derivative of the inner function of the something. So I need to multiply by a half x to the negative a half. And this then needs a little bit of tidying, really. So we've got a half x to the negative a half over x to the half. Now, what happens? Well, we're dividing, so we need to make sure we subtract indices. So what's negative a half take away a half? It's negative 1, so we end up with this, and I can then simplify this to 1 over 2x at the very end. So let's generalise. Now, supposing y is equal to an ln type function, so it's equal to ln of an inner function. The inner function could be anything. ln of f of x, for example. Then dy by dx will equal 1 over f of x, because an ln function will differentiate to 1 over, but we need to multiply by the derivative of the inner function, which is, of course, f dash x. And make sure you can apply that rule quickly and efficiently. So we're going to finish off by having a look at a few examples of differentiation where we may have to use the product and the quotient rule in conjunction with functions that involve ln of x. So my first example, y equals x ln x. Now feel free to either work alongside the video or pause it, try the questions and then come back and check your answers. Now you must be able to identify whether a function is a product, a quotient or a composite. Now in this case it's actually very simple. You can see that this is a product. You can see the two component parts. So u is going to equal x in my differentiation and v is going to equal ln of x. Differentiate both parts. Du by dx is 1. dv by dx is equal to 1 over x. Now, do you remember the product rule? dy by dx, it tells us that dy by dx is equal to u multiplied by dv by dx plus v multiplied by du by dx. So can we now put those components together and complete our differentiation? So what do we know? We have x multiplied by 1 over x, so I'm following this path here, plus ln of x, and I'm going to put that in brackets for clarity, which we're multiplying by du by dx, which is just 1. So this then finishes the question for me, 1 plus ln of x, using the product rule. Question 2, let's take a look at this. And again, hopefully you can clearly see that this is a product, so we're going to need to use the product rule again. So u is equal to the square root of x, but I'm going to rewrite that as x to the half. V is equal to ln of 2 minus 3x. Let's differentiate. Du by dx is equal to a half x to the negative half. dv by dx. Now, here's where we again have to use the quick chain rule. Hence our emphasis on being able to apply the chain rule quickly and efficiently, and why that is so important. ln of 2 minus 3x, it's an ln function. What have we just seen? ln functions differentiate to 1 over 2 minus 3x in this case, but of course we need to multiply by the derivative of the inner function, which is negative 3. So this gives me negative 3 over 2 minus 3x. Now let's put everything together using the product rule. So I want my u multiplied by dv by dx, and then of course we want to add on v multiplied by du by dx, the other way around. So u multiplied by dv by dx is of course this product pair over here. So that's x to the half multiplied by negative 3 over 2 minus 3x. And we're adding on this product pair over here, which is a half x to the negative a half ln of 2 minus 3x. I'm not really sure there's a huge amount of tidying to be done here. We could just rewrite it as a half x to the negative a half ln 2 minus 3x minus 3x to the half over 2 minus 3x. So I've just reversed the order here. So question 3, can you recognise that this is a quotient? So we're going to use the quotient rule. So we need to make sure we can identify the two parts of this. We've got u over v. So u is equal to x and v is equal to ln x. du by dx is equal to 1. dv by dx is equal to 1 over x. And then let's remind ourselves that dy by dx is equal to v multiplied by du by dx. Subtract u multiplied by dv by dx, and then the whole thing is divided by v squared. So let's put everything together. V multiplied by du by dx is of course just going to be ln of x. Subtract u multiplied by dv by dx, which is x multiplied by 1 over x. And then the whole thing divided by v squared. What is v squared? Well, it's ln of x all squared. Tiny bit of tidying, ln x minus 1 over ln of x all squared. Question 4, have a look at it. Now, in theory, with both question 4 and question 3, the product rule could have been applied if you wrote the denominator to the power of -1 and brought it up into the numerator. But as we've seen previously, it is often significantly easier to actually just use the quotient rule here. So let's set everything up. So u equals ln of x and v equals x. So it's the reverse, it's the reciprocal of the previous question. So 1 over x is our derivative of u, and our derivative of v with respect to x is 1. Let's make use of the quotient rule again, and let's go from here. So we want v multiplied by du by dx. Now, we've done this example really already in the previous question, just taking the reciprocal of it. So x multiplied by 1 over x was just going to give me a 1. I'll write that in straight away. Minus u multiplied by dv by dx, so that's subtract ln of x. And then I want to divide by v squared, which is just x squared. Now, question 5, really interesting question, because we could write this as a product and apply the product rule if we wrote it as y equals ln x, ln x. And we could just say u equals ln x, v equals ln x, and then just apply the product rule. And you can have a look at doing that yourself. But it's more interesting to see this as a composite function. You can see it's ln x and it's being raised to a power. So overall, this is a power function. It's of the format y equals f of x, which is some function being raised to the power. Now, what does the quick chain rule tell us to do? Well, let's take a look. The quick chain rule would tell us to multiply by this power. It would then tell us to reduce the power by 1. So that would, of course, become a power of 1, which is just the function itself. And then multiply by the derivative of the inner function. So multiply by 1 over x. So we end up with 2 over x multiplied by ln of x. Remember, differentiating a power function, dy by dx, is n f of x, all raised to the n minus 1, multiply by the power n, reduce the power by 1 to n minus 1, and then multiply by the derivative of the inner function, which is f dash x. And that's exactly what we've done here to get to this answer.